Okay, today's going to be topic 4. This is the 4th video in our 3rd unit, which is all about derivatives. And like I've been doing as I do all of my videos here, I want to remind you what a derivative is, because sometimes kids, they have a hard time wrapping their minds around what we're doing. Like, what is the point of this? It just feels like it's random gibberish that we're writing down. So as a quick reminder, a derivative is an equation for slope. And if you were to have a scenario where let's say that you were plotting something on the y-axis and something on the x-axis, and you had a graph, and it was not linear, it was not consistent, it's something that's going up and down over time. You may want to try to calculate the slope at some point. You'd want to know what that slope happened to be, right? Well, if you cannot calculate it using rise over run, a derivative is useful, because a derivative is an equation for what that slope would be at any given point. You just need to know the x value that you want to plug in, and then you'll have your slope, right? And so I've given lots of examples before, like how much money you make every single day, or what your velocity is over time. I mean, you could even go with like what your voltage is based on distance. If you get like your physics formulas, that would work. So anyways, that's what a derivative is. So we're working now on operations to be able to calculate derivatives of more and more challenging equations. So the first day we learned about the power rule, which basically means drop the exponent down in front and subtract by 1. Yesterday, or last lesson, whenever you're watching these, we talked about how to add and subtract derivatives, and this is what I'm starting our slide with. So the basic rule for adding and subtracting derivatives is if you've got multiple pieces that need to be derived, we'll just derive the first one and derive the second one, and you're good to go. And here's some notations that we use. And I hope that most of you, especially after taking 30-1, but especially moving into calculus, are starting to understand the need for having really good notating skills. You have to be able to record what you're doing very clearly and precisely, so that you know what's happening. Because we have these concepts like a derivative or a composite function, and we have a notation for what it means. It's like a shorthand notation, because I can't just write take the derivative of f of x every single time. That's why we use this notation, f prime x, or dy over dx. It's a shorter way of trying to explain what we're doing. So anyways, let's hop into our first example here. I would like for us to differentiate, which is the verb we use, I guess. Verb, that's the right word. The verb we're going to use for take a derivative of this equation. Right. Now, right off the bat, this is a little bit more challenging because we really have two different, they're not binomials, right? One's actually a, four-nomial, and one's a trinomial. So the best thing for us to do actually would be to factor this out, or to distribute. That's the word I'm looking for. So really what I'm asking you to do is take the derivative of this equation. And I don't want to write in all that stuff again, so I'm just going to say I'm going to take the derivative of that, which really means that I'm asking you to take the derivative of this after you distribute, which is going to give you 6x to the 5, 9x to the 4, minus 4x squared. Oh, hang on, I'm not doing this systematically. I should fix that. Let's see, we'll do, 9x to the 4, then we'll do 12x to the 3, and then minus 15x squared. And then systematically, let's do all by the negative x. So I'll get a negative 2x to the 4, a negative 3x to the 3, a negative 4x squared, and a plus 5x. Then when I times it all by 1, I'm going to get 2x to the 3 and 3x squared and 4x and minus 5. And really, I'm taking the derivative of all of that. So I'll just pause for a second there. Hopefully you were able to follow what I was doing. Essentially, I was just distributing, right? And it's quite the distribution. So one of the things you're going to want to work on is making sure you have a good organizational method to keep track of it. If you're able to figure out what mine was, I did the first row times by the 3, then the whole first row by the x, then the whole first row by the 1. But I lined up like terms in similar columns so that in my next step, when I want to take the derivative, now I'm going to have like terms kind of together, because I'll have 6x to the 5, I'll have 7x to the 4, right? Because hopefully you can just visually see where that's coming from. 12 minus 3 would be 9, plus 2 gets you back up to 11x to the 3. 15 minus 4 is minus 19. Add 3 gives you minus 16x squared. Then you'll have 9x, and you'll have minus 5. Well, now I can apply the rule we learned yesterday. The rule we learned yesterday was to be able to do the derivative of all these things individually. So let's take then the derivative of all these things one at a time, like this. Take the derivative of the 6x to the 5. Take the derivative... Oh, hang on. Let's write this a little bit better. Take the derivative of the 7x to the 4. Take the derivative of the 11x to the 3, and so on. I'm going to have to go down to the next row here just because I'm writing a little bit too large. 16x squared, take the derivative of the 9x, and take the derivative of the 5. Okay, so one at a time using the power rule. The first one is going to give you 30, because 6 times 5 is 30. Drop the exponent by 1, x to the 4. Then you'll have 28x to the 3. You'll have 33x to the 2. You'll subtract, going a little too fast here. 2 times 16 is 32x. Derivative of 9x is 9, and the derivative of a constant term is 0. There is our derivative. So, now that was using, we didn't actually really use any new rules there. We just used the adding and subtracting rules that we've learned before. My goal today is to show you an alternate method of doing this, because this one was reasonable to distribute. It wasn't that bad. I finished this in 5 minutes or so. Right? But what happens if it really is much, much larger than that? What if we're working with things that aren't as easy to distribute out, right? In terms of the, maybe you use the word FOIL, right? This wasn't really foiling because that's just for 2 binomials, right? But if you can distribute this, that's great. But what if that's really challenging? So there's a proof that you can probably find online or in your textbook for how to deal with this without expanding, because that's my next slide here. The example is possible to expand, but there are other ways. And here is the new formula I need you guys to learn. Now, when you get to university, they'll probably require that you memorize this. Okay, this will be something that you're going to have to, like I knew kids who they had all these things on flashcards, because this is one of many derivative rules you're going to learn over the next, as we finish this course. But I will give you this on a formula sheet for your test. So don't feel like you have to memorize this now. Just know that you have to get there later. Here's the rule. If you've got 2 things that you want to derive that are multiplied by each other, the rule is you take the first times by the derivative of the second, and then add the second and times the derivative of the first. Okay. Now, like I was saying a second ago, and maybe got distracted, you can find a proof for this in a textbook or online somewhere, but I'm just going to tell you the rule. And if you really want to see the proof for it for yourself, then you can go look it up yourself. But really, the proof is not the solution. It's knowing how to use this new formula that's important. So what I'd like to do now is I'd like to go back and do this exact same equation. This one I'm showing you right here is the exact same equation, only now I'm going to use what's known as the product rule. And the product rule, just to write it down again, if you have, like, say, f of x times g of x, right, which really we do, right? We have an f of x times g of x. If you want the derivative of that stuff, the rule is you take the first function and you times by the derivative of the second function, and then you add the second function and you times by the derivative of the first function. So here's how this would look, but I'm going to use Leibniz notation because I find that more useful. The first function would be 2x to the 3 plus 3x squared plus 4x minus 5. And then I still have to derive the second function of 3x squared minus x plus 1. Now, I haven't derived it yet, so I'm leaving that d over dx notation there. Then I'll move on to the next part. Then I actually have to leave the g of x function the same way, so 3x squared minus x plus 1. And I'm going to derive the first function, which was the 2x to the 3 plus 3x squared plus 4x minus 5. Now, this is why I'm a big fan of encouraging kids to use Leibniz notation, because there are 2 things that we have to still derive, and there are 2 things that don't need to be derived. The 2x to the 3 plus 3x squared plus 4x minus 5, that one's already done. It does not need to be derived. But this guy right here, the 3x squared minus x plus 1, that needs to be derived. And I'm now going to just do it all in one fell swoop. There's no point in doing it in little pieces anymore. So I'm just going to derive the 3x squared, that's 6x. And I'll derive the negative x to give me minus 1. And then when you derive the plus 1 at the end here, it's 0, so I'll leave it. Then to that, I'll add the 3x squared minus x plus 1, just because this one did not need to be derived. But then I still have to derive the remaining bit. So again, I'll just do this kind of bit all in one swoop now. Rather than writing the d over dx for all of them individually, let's just make this 6x squared plus 6x plus 4. And hopefully I didn't lose you on that step, but if I do, or maybe if I made a mistake, I do make mistakes, make sure you make a note of that, and let's talk later on another day on however it is that we communicate. Well, there we go, we're done. This is our derivative. Now you might say, hey, hang on a sec, that's not the same as what we had right here. However, it is, right? This guy that we had right here is just been expanded out. So we could take the time now just to confirm and make sure I did it properly by doing one last expansion. So let me do that real quick and hopefully you're able to follow. This would give you a 12x to the 4 plus an 18x to the 3 plus a 24x squared minus 30x. And then when you times it all by minus 1, you'd also get a negative 2x to the 3. You'd get a negative 2x to the 3. You'd get a negative 3x squared. You'd get a negative 4x. You'd get a plus 5. And then over here, when you distribute this piece over here, you'd continue by getting 18x to the 4. And then you'd have, let's see, how do I want to do this? Then you'd get an 18x to the 3. And then you'd get 12x squared. 12x squared. There we go. Let's clean that up a little bit here. Got to keep organized, right? Let's see. Then you're going to get a negative 6x to the 3. You're going to get a negative 6x squared. You're going to get a negative 4x. Then you're going to get a 6x squared and a 6x and a 4. Hopefully I didn't make any mistakes in expanding all that. And hopefully you can follow what I did. I was really doing this one times this one, that one, and that one. That's kind of what this row was here. And my method is just to line up all the like terms so that when I'm done, I will have 30x to the 4. Let's see, 18 and 18 is 36. Minus 6 is 30. Minus 2 more would give me 28x to the 3rd. 24 and 12 would give me 36. These guys effectively cancel each other, so 36 minus 3. Hopefully I have that right. 36 minus 3 would give me 33x squared. 30 minus 4 is minus 34. Minus 4 more is minus 38. Bring it back up 6. You should have minus 32x, hopefully. And then that should be a plus 9. Wait, moment of truth. I'm now going to compare these two things, see whether I did it right. Let's see, 30x to the 4, yeah, that's what I had. 28x to the 3, yeah, 28x to the 3. Then a 33 and a positive 33 and a minus 32 are my next ones. Yeah, positive 3 and minus 32. And then constant term is 9. And over here, my constant term is 9. Wait, now you might be thinking to yourself, okay, that wasn't actually easier. Right? That was still a lot of work. Look how much distributing you had to do, right? All of this work right here, there's so much distributing I had to do. But here's the thing. We developed this rule because we would actually accept this right here to be our final answer. We could have stopped right here because, see how these two derivative signs were sitting in there? Well, once we've taken all of the derivatives necessary, we don't simplify usually in calculus. We don't see the purpose in expanding things out like crazy, because that's just a busy work sort of task. The assumption is that you should be able to do it if you need to, but this doesn't add any extra value by expanding all this stuff. So we actually would have stopped right here and said our derivative is equal to this. And if you want to expand it, I mean, go ahead. That's your prerogative. You can if you want, but it doesn't add any mathematical value to expand it out. And so that's where the product rule becomes nicer then, is that this is now our derivative. This is still an equation that would give you the slope at any point. You just need to know what x is. I mean, you'd have to plug in x here and here and here and here and here and here, but this still would be an equation to get you your slope. So hopefully that made some sense. If I lost you, again, like I always say, rewind, watch the video again, watch it in slow motion or in double time, or write down your list of questions to ask me. But I'm going to move on to a few more examples then. So example 3. Now let's differentiate this guy. Well, we could try distributing, but I mean, now I'm working with square roots getting distributed in. There's a better way. So using our new product rule. The product rule says to find the derivative of f of x times by g of x, that is equal to the first times the derivative of the second plus the second times the derivative of the first. That is the new equation for our derivative. Now I got to point out, I'm being very purposeful with my brackets here because all of the 2 minus 3x, that all has to be derived right here. Really, what I have to do is I now have 2 derivatives I have to take. I get to leave the root x, and I get to leave the 2 minus 3x in those locations. Those aren't changing spots. Like, those are things that just need to be left as is. And now I need to take the derivative of this guy here, which I'll do in purple. And I need to take the derivative of this guy here, which I'll do in red. Well, 2 minus 3x, when you derive the 2, it gives you 0. And when you derive the minus 3x, it gives you minus 3. So there, I'll just make sure I'm timesing by minus 3. And then this guy right here, I mean, if you know the derivative for a root x, just go right to that. But maybe you might want to simplify it and like rearrange it and call it this is x to the 1/2. Right? And I love this notation because if you're not yet ready to take the derivative, then just leave the derivative symbol sitting there. So, I mean, this is not bad. I can actually rearrange this first term to minus 3 root x plus 2 minus 3x. And then maybe now I'm ready to take the derivative. That'll be 1/2 of x to the minus 1/2. At this point here, you are done. This is valid to being finished. There's no point in going any further.
For a phone call, Kelly?
Haven't had an announcement on one of my videos in a while. If you wanted to, you could rearrange this. You could put like the 1/2 in front. And then you could say, well, x to the minus 1/2 really means 1 over the square root of x. Like, if you wanted to rearrange it, there's no problem with that. Like, that would work. But honestly, this first step that I was underlining right here, this is where I would be content with you stopping. And in fact, I actually want you to stop there because you're not changing the derivative. You're just rearranging it algebraically, which is fine. Sometimes there's some value to that. When we eventually get to a spot where we now need to solve this, when we then say, well, I want you to tell me when the slope is 3, then you're going to want to do some algebraic manipulation. But if you're just looking for a generic slope based on an unknown x value, really just stop up here. So this then would be a little bit more specific. Now I want you to find the slope of the tangent to this graph, but now I'm actually going to give you the point. So rather than just looking for the generic derivative, when we're done with this derivative, then we'll actually plug in a number to calculate the slope at that point. So this graph right here, hopefully you look at this and you know that this graph right here was actually a graph that was to the power of 5. It happens to be written...
The office for a phone call, Kelly?
This happened to be written in like a factored format. And if we wanted to, we could distribute it all out. Or let's try using this product rule. So the product rule is the first binomial, let's put it in a bracket, times the derivative of the second binomial plus the second binomial in its undifferentiated form, and then multiply that by the derivative of the first binomial. Right. And when I'm working with my kids in a classroom, I'll then pause at this point and I'll say, well, how many derivatives do you still have to take? And hopefully they'll be able to identify that we have to take 2 derivatives. There's one right here, and 1 right here. As soon as all of your derivatives have been taken, we're done. We can stop, at least in terms of finding the derivative. Right? So, to find the derivative of this equation, it'll be, you still have your 3x plus 2 in brackets. And then the derivative of this guy is going to be 6x squared. Right. Drop the 3 down in front, times by the 2. Pop the 3 down to a 2, and then the constant term derives to 0. And then you got 2x to the 3 minus 1. That doesn't change. But then when you want to derive this guy right here, it's 6x. Right? Drop the 2 down, times by the 3. Drop the exponent of the 2 down to a power of 1. And then this 2 is a constant term. It has no slope. Okay. Now, this is our derivative. If that's all I had asked you for, we are done. However, that's not what I asked you for. In a fancy way, I asked you for f prime of 1. That would be another way I could notate this. I asked you for, find me the derivative, but we want to plug in 1. And this is where this notation is kind of useful, because this kind of is a good way for me to show you that I want you to now let all of your x values, we want to let all of our x values now be 1. We want to find out, well, what is the slope when x is 1? So 3 times 1 squared plus 2 in that bracket would give you 5. And then 6 bracket 1 squared in this kind of section here would give you 6, which gives you a running total of 30. And then over here, you've got 2, 1 to the 3 minus 1, which is 1. And then you've got 6 times 1, which is 6, giving you a running total there of 6. So for our final answer, it's 36. And you could notate this as f prime 1, basically saying I took the derivative of my function, then I plugged in 1 and I got 36. You could just say that the slope is 36 if you wanted to. Or honestly, in a question like this, if you just said the answer was 36, I'd be okay with that too. Because I said, well, what is the slope? The slope is now 36. If you were to take this graph right here and graph it in your calculator, I don't know exactly what it looks like, but just a rough idea. It's a power of 5. What's that, a quintic? So it probably looks something like this. Wherever x was 1, which would be right about here, this is where x would be 1. The slope right here must have been exceedingly high, very steep at that point. Right? And that slope obviously changes as the graph goes along. So, okay, normally in class I'd ask you if you have any questions, but obviously you can't respond. So if that didn't make sense, rewatch. Ask me questions. Email me. Please email me questions so that I can try to help. Okay, well, this brings us to our next concept here. What happens if we're trying to divide? Right? Now, multiplying has its own rule, but division is a little bit different. Now, there's 2 ways you can approach this. One of the ways you can approach this is to say, well, this is really x squared plus 2x minus 3, and it's x to the 3 plus 1 all to the minus 1. Right? Because that negative 1 exponent around this guy really brings this guy back up to the top of the equation. And hopefully that made sense to you, because that's a basic exponential rule. The problem is that this method here, although it does look like, yes, we're multiplying things, we do have a second exponent up top here. And this is going to involve the chain rule, which I'm going to show you in your next video. So although this is a method that could work, we need to pick something different. We need to know what the rule is for dividing things. And that's actually on my next slide here. This is the quotient rule. So this is the rule that we use when you have to divide things. And it's very similar to the product rule. It's got a lot of similarities to it. You take, like, say, one of the 2 parts, you know how there's like an f and a g. You take one of them, and then you multiply by the derivative of the other. And then here you take the original of the other, and you times by the derivative of the first. There's some similarities here, except the order is different. Because when you're dividing, there's the numerator and the denominator, it makes a difference which order you do. So it always has to be denominator times by derivative of the numerator minus the numerator times the derivative of the denominator. And then the other thing is that it's all over the denominator squared. So that's my note right here. Order is vital. If you don't do these things in the right order, you don't get the right derivative. Okay, now, if you're wondering, where the heck did this formula come from? I can find you a proof of how this was discovered, how this was created. You can probably find one in any textbook, right? But that's not the important part. You're not being assessed on how the proof was discovered, because honestly, like, if I were to ask you to prove how this was done, I would never expect you to do this. Like, this was something brilliant done by, like, say, Einstein, or not Einstein, Newton or Leibniz. You know, some really famous mathematician managed to come up with this. I wouldn't expect a grade 12 student to just be able to figure out where this formula came from. I would expect you to be able to follow a proof for how this occurred, but I mean, this is the basis upon which calculus was made. So don't feel bad if you're like, I don't know where that formula came from, because honestly, I don't either. Right? I can follow it. I can understand how the proof came to be if you show me the proof, but to come up with that on your own, I mean, that's what mathematicians did and do. So okay, let's do this example here. If I want to find f prime x, the derivative, the formula is. And maybe I'll use capital F actually, just so that I can use like F being the top and G being the bottom, like little f and little g. So the formula is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Right? Write down that formula somewhere nearby or keep it handy. I won't make you memorize it for your midterm. I'll give this to you on the cover sheet of your midterm. But we've already now learned actually a couple of different formulas. I mean, there's the one for adding and subtracting, which you probably don't even need the formula for. But now there's one for multiplying and one for dividing. We're going to learn another one later for what's called the chain rule. And then we're going to learn formulas for how to derive things that are not polynomials. So when we have to derive things that are exponential and sinusoidal and logarithmic, we got tons of formulas for that too. So anyways, I digress. I'm getting off topic. Let's give it a try. We need g of x as is. So x to the 3 plus 1, write it as is. Then we need the derivative of the top. So, I mean, I'm going to do this in stages just to make sure I don't make a mistake. So I'm not ready to derive the derivative of the top yet. I'll get that in a second. Then we subtract the top. As is. Then we derive the bottom, which was x to the 3 plus 1. And then that is all divided by the bottom squared. Well, then at this point here in my typical class, I'd look at the students and I'd be asking them, how many derivatives do you have to take? And the answer is 2. And some kids, they look at this point here and they get freaked out and they go, oh my goodness, look at all the work I have to do. But really, you're most of the way done. All you have to do is derive this and derive this, and we're going to call her quits. There is no point in trying to distribute and factor and do all that other mess, because that is just a pain and it does not add any extra value right now. So I'm just going to start taking the derivatives of the 2 derivatives that are required, and I'm going to leave everything else where it is. Right? All of the other terms that don't require a derivative, I'm just going to leave them. Now, I mean, if you wanted to, you could distribute that. You could distribute this. You could distribute this. You could subtract them from each other. You could see whether you could do some canceling and factoring. And that might be useful. But we were asked to find the derivative. We've done that. This is an equation for the slope of the previous graph. If you give me an x value, I can plug that into the equation and find you the slope. Right? So simplifying, it's not necessary. So if you even look at my assignment, I believe, one of the first questions where I ask you to take derivatives, I believe it says, do not worry about simplifying. I don't know how I phrased it, but I don't need you to simplify. Now, that being said, if you were to use some textbook questions, which I highly recommend you do, you should do some more practice on this than just the examples I have in my book. In fact, I'm going to try to give you guys a list of possible ones to try out of the standard textbook that our division, I think, has. It's a red one by McGraw-Ryerson company. But I mean, honestly, any calculus textbook will give you lots of practice examples. Anyways, the point I was trying to make before I got myself distracted is that if you check the answer in the back of the book, they may write it in a simplified form. They may actually choose to distribute this out and subtract and distribute this, and maybe they even refactored and canceled some stuff. But I'm content here. And you're going to want to ask your university professor what they're looking for. This really depends on who is marking. So make sure when you get to first year calc next year, ask and say, hey, at this point here, is this sufficient, or do you want me to go further? And I mean, if they want you to go further, well then fine, then distribute it. That's grade 10, grade 9 algebra. I mean, I know you have those skills. It just sucks because it's a lot of work, but you know how, obviously, right? My expectation, stop here. Okay, I think I have just one last example here. Yeah, this is my last example. After that, we're going to talk about the chain rule, which is, like I've been hinting towards over the course of these videos, the chain rule is probably one of the most important things that university professors are looking for when you're doing calculus. So, okay, one thing you could do, by the way, is now if you feel like you got the hang of it, maybe pause my video, try example 6 without me doing it first, and then watch it afterwards. You could watch it on fast forward if you want at that point. Like if you feel like you have the hang of it, I mean, at this point here, all I've got left to do is just more examples to try to further your understanding. If you understand, you may just want to call it quits. So really, this is up to you. At this point here, I'm just going to do one more just to make sure it's clear. So I'll probably narrate a little bit less than I have in the past. The formula for this is, let's see, you got to get it right. It's denominator times the derivative of the numerator minus the numerator derivative of the denominator over the denominator squared. Okay, bottom, 1 plus 2x. Derivative of top. Not quite ready to go there yet. Top. Derivative bottom. Bottom squared. Just want to make sure I wrote the formula down right, because there's nothing worse than writing the formula down wrong. Okay, now I'd ask, well, how many derivatives do you need to take? And the answer is 2. Hopefully by now you know how to derive the square root of x. It's 1/2 x to the minus 1/2. And then hopefully you know how to derive 1 plus 2x. It's actually just 2. 1 derives to 0. 2x derives to 2, right? There, we are done. So one of the big changes in this section here is it's less about the puzzle where you're supposed to have the big aha moment where you're going, oh yeah, I see what you did there. I mean, you'll hopefully have a couple of those here and there on certain types of questions, but you do need to get your your practice in. So email me. If you'd like me to send you some more practice questions, you should do those. Because on your assignment, and maybe I'll just pull up the assignment so you can see it now. Here's the assignment you're going to be working on. The very first question is basically find the derivative of these functions, and I don't even want you to simplify. Right? And I'm really giving you just a little snippet of practice. I'm giving you one that's pretty straightforward here, just power rule. Here's one with quotient rule. This one's actually going to require the chain rule, so you may need to hold off on a few of these. Here's a product rule. Here's a quotient rule. This will be a chain rule here. But really, 8 examples is not enough practice. It's not. You need more. So find a textbook, find a work pack. Chapters in Lethbridge will sell a wonderful workbook called the Snap Workbook, which has so many practice questions, but you really need to get some practice questions in. So anyways, that's it for my lesson for now. As I always say, I need for you guys to get a hold of me, okay? Be advocates of your own learning. Don't be a passive learner, especially when you get to university. Know some strategies about what to do when you get stuck, because you're going to get stuck. So be comfortable in talking to your teacher or professor. Find a study group. Know where to look online for help. Use a textbook for help. I have resources that I'm giving you here, but I need to encourage you guys. Ask me more questions. Utilize our Thursday video chat time. If that doesn't work for you, make arrangements for something more. But don't just sit back and be like, yeah, I think this will work out, because it gets harder, guys. I mean, this is just leg 1 for many of you of a 4-year university career. And you need to start building solid, healthy learning habits now while you can. So, okay, my little lecture and rant is over. I'll stop the video. This has been about half an hour. we are most of the way done the unit. So hopefully you've watched all these 4 videos so far. You're now ready to start doing some of the assignment questions. So, okay, we'll talk to you guys later.